longer lying to me, Maddie, and toying with my emotions. She promised me she was done. All right, so last time we were working on page 288, number 25, and we did part A. And what we had was the Earth, and we were trying to figure out what the angular speed was at the surface at a point that was at a latitude of 40 degrees north. So we talked a little bit about what latitude meant. And we also reminded ourselves that if we think about the Earth as being a rigidly rotating body, which it's not, but we're going to pretend it is right now, that the entire thing has the same omega. So we knew that it went all the way around, which would be 2 pi radians, in 24 hours, and then we were able to figure out what omega is. Okay? Shh. Yeah, I'm teaching the class. Okay? So that was part A. And what's part B? 288. Okay, so I'm still looking at my point up here, but now I want to know what the linear speed v is. And so what we did right before we started this problem was to talk about the relationship between linear or translational quantities like s or x and v and a, and the angular quantities, which are theta and omega and alpha. So how are v and omega related? So I'm talking about velocity. Yeah, but can't you just tell me what v is equal to? Omega r. Which we use to make the relationship that I think you were talking about, which had to do with centripetal acceleration. But this is really what our answer is. Okay? But there is a tricky part here. What is this r? It's a radius that we measure from where? The axis of rotation. So this distance here is actually going to be r. It's going to be the shortest distance from the axis of rotation to where that piece is. So it's this distance here, which is different than this r here, which is the radius of the Earth. Okay? So we're going to have to do a little geometry. So let's just kind of rewrite some things here. Here's going to be my North Pole. Here's going to be my equator. I guess is black. All right, so here's going to be my point up here that's at a distance, capital R, the radius of the Earth, from the center of the Earth. It's at a latitude of 40 degrees, and we said that was the angular distance above the equator. But what I'm really going to want here is little r. So how do I figure out what little r is? Which angle? Okay. You could also have said alternating interior angles. Okay. So then how do I figure out what little r is, Priya? I know what this length is. Because you don't have your glasses? Yeah, come and point, Priya. Okay.
We don't have this one.
No.
Okay, so we have this
It's going to be capital R times cosine 40. Zoe, do you agree? Okay. And then capital R is going to be the radius of the Earth. And I'm going to tell you, just because we're running, I don't want to run out of time today, that the radius of the Earth is 6.37 times 10 to the 6th meters times the cosine of 40 degrees. And what are we going to get? Let's see what other people get. Priya got that. Sarah, you got it too? Okay. So, remembering that what we're really trying to find here is V. So I've got V is going to be omega, which was 7.27 times 10 to the minus 5 radians per second, times little r, which is 4.88 times 10 to the 6th meters. And what's V going to be equal to then? Sig fig, Zoe. Do I have 3 sig figs? We might have 3 sig figs. 355. I need to get through the material, Priya. Okay, so this is one of those situations where the radians don't have to cancel, they just go away. All right, like we talked about, that the radians are just saying, hey, I'm an angle, remember, I'm an angle, but they don't actually have to cancel with anything. If it had been revolutions per second or degrees per second, that would have had to be a unit that would cancel. But we don't say it's 355 radian meters per second, it's just 355 meters per second. No, radians will always just go away because they're not a real unit. They're, like I said, an indicator. They're just a reminder so that you know in your heart of hearts that it's an angle. Okay? All right, how about C and D? What do C and D ask us to do? The equator. Okay, so again, here's my Earth, here's my equator, and now I've got a point here. So really, for part C, omega is pretty easy, right? Because what do I know for a rigidly rotating object, Maddie? Omega is the same no matter what. So this is going to be 7.27 times 10 to the negative 5 radians per second. Right? We all agree? All right, so part D is to find what? Linear velocity, which is V. And what is linear velocity equal to? Omega r. But what's r in this case? It's just the radius of the Earth, because here's the center of the Earth. There's my rotational axis. And so that r is in fact equal to the radius of the Earth. So V is going to give us our 7.27 times 10 to the negative 5th radians per second times 6.37 times 10 to the 6th meters. What'd you get, Sari? Okay, others got that as well? Good. Okay. And again, the radians just go away. They don't have to cancel with anything. But revolutions or degrees would have to cancel. All right. Okay, we good? It's just kind of a plug and chug. Let's try something that is going to take a little more thought. So let's try page 288, number 28. If somebody would read it for us, please. Okay, so here's my wheel A with radius RA. Here's my wheel C with radius RC. And they're connected by a belt. I don't really know why the belt has to have a letter because the belt isn't really going to do anything. I'm not going to refer to the belt. There's no R belt. Okay. And there's a hint, a very important hint. And what does the hint say? So that tells you that VA at the radius, out here, has to be equal to VC at its outer rim too. Because I could have a linear speed anywhere. I could have a linear speed at R over 2. I could have a linear speed at 0.1 R. It does make sense because the belt is one thing that's moving and it's got to move together. Similar to, I think, actually, and we'll come back to this in a little bit, how the linear velocity of a pulley has to be the same as the linear velocity of the things going up and down, right? Because it's all one string that's connecting the whole thing. Just saying. All right, so you have seen this before. So, I don't know. I look at this problem and I'm kind of like, I'm not real sure where I'm going to go with this. So, what do we do when we look at a problem and we're not real sure what we're going to do? We've drawn a picture. We've drawn our picture. We've taken into account this cool thing that we know. Okay? And I know it feels like this period should be over, but it's not. 11:56. Of course. Of course. I should have just gotten up and left, Johnny. I would have assumed you were going somewhere important, as I always do. All right, so we know some things for wheel A, and we know some things for wheel C. Let's see what we can figure out here. All right, so what kind of info do we have? Zoe, give me one thing. Okay, so alpha A is 1.6 radians per second squared. It's just for A. I think. At least I would not feel comfortable at this moment in time of assuming that it was the same for both. I'm pretty sure it's just for A. What else we got? What else do we know? Maddie. Yes. Because if one of them is starting from rest, the other one has to start from rest. Because they have to have the same linear speeds at any time. What else do we know in here? Okay, so I know that RA is 10 centimeters. Chances are we can probably leave it as centimeters. What else? So, okay. There's at least two more things we can put in here. It is, but I'm not really concerned about how many times it's going to turn, because that's not part of my question. You are correct, but I think it's extraneous information. But there's two more things we can put up here. Okay, so the radius for C is 25 centimeters. And there's one more thing. What so? Okay, so we're probably going to have to convert that. At least convert the revolution part, because I really can't mix revolutions and radians. And actually, I'll have to do the minutes too, because I've got radians per second over here for the acceleration. Sure. So we'll take a little side trip. And we'll take our omega CF is, what is it, 100 revolutions per minute. So we'll do the easy part first. 1 minute is how many seconds? And one revolution is what? Yeah, because it's one complete trip. So whether one complete trip is one revolution, 2 pi radians, or 360 degrees, in this case I want it to be 2 pi radians. So if we do all that out and do all the math, what do I get? Let's see what somebody else gets. Lisa agrees. Sarah, did you get that? Okay. So we know we've got that. Everybody copy down what they need? Yeah? Okay. So I know that this is really 10.5 radians per second. So I think that's all the information. So maybe it's time for a find statement. What are we supposed to find? No. Find the time. Okay? Between our initial state where everything's at rest and our final state over here where wheel C is moving at 10.5 radians per second, is rotating at 10.5 radians per second. So wheel C is the only place where I have an initial condition and a final condition. And you want to find time. So again, what kind of equation is percolating through your head here? Okay, so omega, in this case, omega C final would be omega C initial plus alpha C times time. But you're right, I need alpha C. Do I have any kind of alpha? What do I have? I have alpha A. So what would happen if I applied this equation to my A column? I'd have omega AF would be equal to omega AI plus alpha A times T. So I know what this is because it's 0. I know what this is because it's given to me. I want to find that. So if I could take some kind of side trip again and find omega A final, then I could use that equation and find the time. Either way, I have to take a side trip. But as the omniscient narrator, taking the side trip over here to find omega AF is probably going to be easier. So do we have any ideas on what that side trip will involve? I don't have any positions, so I'm not going to be able to use that. We can't use anything else from chapter 2 or what has become now chapter 10, but right. And we usually, when you're using the equation for a period, you've got something that's moving at a constant rate, and we don't really have something rotating at a constant rate because it's starting from rest and speeding up. Have you used all the information you have? Okay. No, that's what Zoe was talking about with the period, but usually with period, it involves a constant rotational rate, so omega would have to be a constant, and it's not. I don't really have an equation to be taking the derivative of. Have you used all the information that you've been given? Yeah. So if we take our side trip here, so I know that VA at RA is going to be VC at RC. And if I think about it at my final time, as it were, okay, then what's VC equal to? Yeah. And what's VA going to be equal to? Yeah. So you know 3 out of 4 variables, and the 4th variable is what you're looking for to help as part of your side trip. So omega AF is going to be omega CF RC over RA. Should be an F there. So omega CF is what we figured out at the top of this page, 10.5 radians per second. Omega C is 25 centimeters. Omega A is 10 centimeters. And what do we get? Let's see what others get. Sari agrees. So does Elisa, so does Priya and Maddie. All right. So that was pretty cool. So now remember what we were really looking at was omega A final was equal to omega A initial plus alpha A times T. And we know that it starts from rest. So we know that omega AI is 0. And so I can solve this for T, and I get omega AF over A alpha. So I've got 26.3 radians per second divided by 1.6 radians per second squared. And what's that going to give me for my time? Yeah. So Priya gets 16.4. Zoe, what did you get? Sari, good. Maddie didn't. But you should. So there you go. Okay. All right, so you get it? And it was a nice review of what do we do when we come to a problem and we don't know what to do. Okay, you got to work through it. You have to use the algorithm that we've been talking about all along, drawing your picture, collecting your knowns, making a find statement, looking at your equations. Okay. All right. So as I've said a couple of times, chapter 10 and 11 is really about taking everything that we did in chapters 1 through 9, except that now we're going to do it for things that go in circles. So the next thing I'd like to talk about is rotational kinetic energy. So if I want to find the rotational kinetic energy of some body that's rotating, so here's my axis of rotation. Then I really need to add up the contribution from each piece. So I'm going to say that this piece has a mass mi, it has some linear velocity or linear speed vi, and then I would say that my kinetic energy was the sum of all those pieces. And then what's the formula for kinetic energy? So I'd have 1/2 mi vi squared. And that's my summation symbol again. We've come across it before. It just means that I add up all the contributions. I've got to take my disc or my wheel or my sphere, whatever it is, break it up into infinitesimally small little pieces, figure out what each speed is, figure out what its mass is, and add them all up. Which sounds like a pain in the neck. Because at every radius, I have a different linear speed, right? Right? But what's the same for every point on my object? It's a rigid body. The omega. So if I could somehow turn this into omega, that would help. So here's my omega. It's turning that way. And I'm going to say that my little point, my little mass mi, is at some radius ri. So how can I write vi in terms of omega and ri? So v is equal to omega, in this case, times ri. Now, I know it can be confusing to remember whether v is equal to omega r or v is equal to omega over r, but it's helpful to think about the units. What are the units of omega going to be? Radians per second. And Sari, what are the units of r going to be? Distance. So what? Meters. And Elisa, what do I need the units of v to be? Meters per second. Yeah, just meters per second. So if it's meters per second on this side, it has to be meters per second on that side. Omega, like you guys said, are radians per second. R is in meters. So I have to multiply them if I'm going to end up with meters per second. Okay, just a way to kind of check yourself. But this will help you. Okay, so I can rewrite my equation for kinetic energy then. I can say that kinetic energy is that sum over all my parts I, 1/2 mi times omega, erase that so there's some space here, omega ri squared, right? Just substituting in for vi. I'm going to pull out my 1/2 because it's in every term. So then I have my summation over I of mi ri squared. And I'm going to pull out my omega squared because, again, that's in every term. So this part here tells me not only what the mass is of my object, but how that mass is distributed. It's the same for every term because omega is the same for every point on my rigidly rotating object. Okay. So, like I said, what I have here not only describes what the mass is, but how it's distributed. So if I had a bike wheel and I had a bike wheel with 2 tennis balls in it, stuck in the spokes, that wheel would rotate differently than my wheel that didn't have the bike, that didn't have the tennis balls in it. If I had a solid wheel versus a hoop, those two things are going to behave differently because their mass is distributed differently. If I put the 2 tennis balls next to each other, or I put the tennis balls across from each other, it's going to make the wheel behave differently because the mass is distributed differently. Okay. And this quantity is actually really important. And for a lot of symmetric objects, we can easily figure out what this is going to be. And so we call it something, we give it a name. It's called the rotational inertia. It's just the bracket. Sometimes, especially if you have an older teacher, they might call it the moment of inertia. Moment is a physics thing. You can have a dipole moment. You can, it's a measurement. Okay. So that means that I can rewrite my kinetic energy formula again. And now it's my rotational kinetic energy is 1/2 I omega squared. And if you think about it, it kind of makes sense. Because what's the formula for kinetic energy? 1/2 mv squared. So here's my 1/2, here's my m, here's my v squared. You got to do something a little different because, like we said, when things are rotating, it matters how the mass is distributed, not just how much of it there is. So if you look at table 10.2, I don't know what page it's on. Page 270, what's 270? 274, okay? So Priya, you should be opening your book to page 274. All right, that gives you the rotational inertia for a bunch of common objects. But notice that it's really important what the rotational axis is. So for instance, if I take a rod and I rotate it around its central axis like this, so it's like I'm twisting my pen. Okay, what's I going to be for that from your table? One half mr squared. But what if instead of twisting it this way, I twist it this way? No. So now, again, I have my rod, but now my axis of rotation goes like this. Okay, so it matters not just how much mass I have, but how it's distributed and where the axis of rotation is. Okay, so I just want to say one more thing. I shall save it for Monday. Have a lovely day and a lovely week.